Hello, everyone. Hi, Claudia. Welcome back from the lunch break. Our next speaker is Professor Claudia Diaz from KU Leuven in Belgium. Claudia has graduated from Leuven, the same university, but then I think it had a different name when she graduated from it. And she's an expert on anonymous communication. She served as the program chair for PETS, Privacy Enhancing Technology Symposium, and I think she's serving as the program chair for Financial Cryptography 2021, well-known venue for discussing how money and anonymity and cryptography go together. It's a great pleasure to have Claudia with us. Claudia, the floor is yours.
Thank you very much, Or. I will stop the video and share my screen if that's okay.
Yes, but you can leave the video if you like. It shows a small video for most of us. Okay. And one thing I forgot to mention, please put your questions into the Q&A or the chat, and we will ask Claudia throughout the lecture or whenever possible. And you can also send them to Sophia by OTR version 4, but only to Sophia, and then she will send me an email, and then I will read the questions. So, referring to the previous talk, Claudia, everything is fine. So, thank you, Claudia.
All right, so a slideshow, presenter view. If I do like this, does it look good? Or do you see like the presenter view as well?
Everything is fine, it looks great.
It looks good, okay, thank you very much. Okay, so thanks all for the introduction. I'm Claudia Diaz from KU Leuven, and I will be talking about network anonymity and mixnets, just giving you an introduction to the topic. And now that of my talk, I will start by motivating the need for network anonymity, talking about traffic analysis and the threats that it poses to privacy. And then I will go into looking into the building blocks of anonymous communication systems, notably mixes are kind of the basic building block of mixnets. And then I will review all the different elements that need to be considered when designing mixed networks, meaning anonymous routing, dummy traffic, and so on. I will then discuss the two main attacks on mixnets and conclude with takeaway points. I have 30 slides, so I'm hoping there will be time for questions at the end. All right, so what is traffic analysis? It basically is making use of what is called traffic data to extract information about what people are doing. And this is in contrast to interception or cryptanalysis that looks into the actual data content and tries to make sense of what the original data is, tries to recover the original data. So what is traffic data or network metadata? And I will use these two terms interchangeably. Metadata can be more general than network metadata. You can have metadata for database records in a database and so on. But here I'm talking about network metadata, which is the same as traffic data. So what this data includes is things such as the identity or call signs of the parties that are communicating, how long they talk, the duration, the length of transmissions, when they are talking, in which location they are sending or receiving packets, and again, no content because it may be encrypted. So in traffic analysis, basically, we assume that content, we can get nothing out of it. Encryption is perfect. We are not considering any cryptanalysis attacks, thinking that that also all works perfectly well. And instead, what we do is that we look at this metadata and try to see what can be learned from it. So you might think, okay, well, just metadata was a big deal. It should be much less sensitive than content because what you're saying is really the sensitive thing. But just to give you a sense, I have 3 quotes here. So the first is from Diffie and Landau from their book, Privacy on the Line, on the politics of encryption. And they say that traffic analysis and not cryptanalysis is the backbone of communications intelligence. The reason why they say this is that traffic analysis allows you to get an iBird's view on what the different participants in a communication system are doing. What's the communication graph? Who's friends with whom? Who are the nodes that have more centrality maybe in an organization, and so on. So it's actually extremely powerful as a technique. Stuart Baker, who was the NSA General Counsel, went as far as saying that metadata absolutely tells you everything about somebody's life. If you have enough metadata, you don't really need content. So that's extremely powerful.
Claudia, I'm terribly sorry for interrupting. It seems like you're in the presenter view, which is a bit small according to someone, to Chaim.
All right, yeah, that's what I was asking.
The second display, so it will show the screen view.
Yeah, so like this?
Yeah, that seems better. Thank you very much.
Okay, yeah, no problem. Yeah, that's why I was asking before, because I was wondering if you see the same as me or if you see what should be on the big screen. All right, so yeah, the problem is that now I need to, yeah. Metadata absolutely tells you everything about somebody's life, and if you have enough metadata, you don't really need content. So this gives a sense of how powerful metadata can be when trying to infer what people are doing or what their function might be in an organization. And quite infamously, Michael Hayden, the former director of the NSA and the CIA, said, "We kill people based on metadata." I believe this was in the context of targeted assassinations in Yemen, I believe, where they were basically looking at people's locations and who they were associating with and making decisions based on that, on whether those people should be targets. Okay, so metadata is extremely revealing. So how easy is it to collect it and to exploit it, right? So the problem with metadata is that it's exposed by default in all the core internet protocols, TCP/IP, HTTP, FTP, TLS, even the ones that have security like TLS and DNS and use encryption still expose the metadata, meaning the to, the from, the time when the message is sent, the length of the message, even if there is a little bit of padding, usually that is not enough to completely conceal message length. Furthermore, it's not only exposed, but it's available to a very large number of intermediaries. So that starts from your local provider. It could be whoever is controlling the Wi-Fi router you're connecting to, or the local network, then going to the internet service provider that is providing you with access to the internet, or the mobile network operator where you're connecting with your mobile phone, going to the big entities in the core internet infrastructure, such as BGP routers, autonomous systems, internet exchanges, and so on. And of course, also including internet backbone cables that, as we know, were actually revealed to be wiretapped by the NSA in some of the Snowden documents. So any intermediaries that have access to the network at any of these points will be able normally to collect metadata and exploit it. Now, furthermore, metadata has lower legal protection than data content. So while it is illegal, for example, to listen to somebody's phone call or to open somebody's email without court orders, it is much easier to get their call list without needing like very stringent authorizations from the judicial power. So that means that it is relatively easy for a number of entities to access data without, without the protections that we have for content being there to protect it. Another thing with metadata is that it's machine readable. It is lower volume than the content we transmit. If you think of, for example, downloading a YouTube video, the metadata would basically be the time when you watch it and the URL and the length of the video. So that's a lot less than the video itself. And it's not only lower volume, but it's much easier to analyze automatically than content, because, I mean, making sense of human language can be very difficult for machines to do adequately. There is a lot of context, there is a lot of usage of language that might be, special between closed groups of people and so on. But metadata is speaking the language of computers, is in times, is in IP addresses, is in number of bytes. So it's incredibly easy to feed to machine learning algorithms or to any analytics and to make sense of what is going on, what patterns we can infer from how people are communicating and therefore what they might be doing. And as we will see, it's in the next slide when I talk about what it takes to design anonymous communication systems, it's actually rather difficult and expensive to protect, as opposed to cryptography, which with today's computing power is extremely effective in protecting content with very high security. So there is a lot more, we are a lot less advanced in terms of protecting metadata than we are in terms of protecting content. Okay, so let's move to anonymity. Anonymity, the first definition that we use from anonymity is from Pfitzmann and Hansen. They proposed this definition in 2000, which is kind of the moment that a lot of research starts being done in privacy technologies and anonymous communication systems in particular. And they define anonymity as the state of being not identifiable within a set of subjects, which is called the anonymity set. So, I mean, what is interesting about this is that before this definition became really widespread, people had this intuition that the idea of being anonymous is that either I know your identity or I don't. So it's kind of a binary thing. Either I know who you are, and then you are identifiable, or I don't, and then you're anonymous. And what this definition does is to kind of change the frame for thinking about anonymity, saying it is not about whether I know your name or not. It's not a binary, but rather it's about how much uncertainty I have or about who you might be. So it's more of a model like this, by which we have an anonymous user that we don't know the name. That's why this user is anonymous, and we have a set of names that might be the correct ones for this user. So this Alice, Eve, David, Fiona, Carol, Bob. This is our anonymity set. This is the set of people who might possibly be our anonymous subjects. And what is important here is that what this conveys is that anonymity requires you to hide in a crowd. So you cannot be anonymous on your own. You need other people. You need to be confused with other people. And the anonymity comes from somebody not being able to pinpoint whether the anonymous subject that sent a transaction, sent a message, accessed a website, or conducted any sort of online transaction, who that person is within the possible set of subjects, okay? Here I put in parentheses diverse, and I believe that diversity in the anonymity set is extremely important, in the sense that if you have a group of people that is extremely homogeneous in your anonymity set, then the fact of belonging to this anonymity set might be very revealing for an adversary. So I give you an example. Imagine that the police is using an anonymity system in order to infiltrate criminal markets and gather intelligence about what people are up to in these markets. If we have an anonymity system that is used at police stations, so that you don't know which agent might be the one currently entering the system or checking out the system, that is not terribly useful, because from the adversary's perspective, if it's enough to know that the anonymous user is a policeman, that might be already enough to know that they need to show fake information or take some sort of action. It doesn't really matter whether it is Agent Alice or Agent Bob or Agent Charlie. What matters is that this person is belonging to a certain group. So if you don't want to have that kind of group characteristics allow for inferences about the anonymous subject, then you need diversity. If all sorts of people are using your anonymity system, then the fact that somebody's coming out of this anonymity system, contacting you through this anonymity system, doesn't tell you much about who that person might be or what kind of attributes or identity attributes that person might have. And the other important point here is that anonymity becomes, as I said, not a binary, that either you are or you're not, but is more of a slider, is more of you can be more or less anonymous. And you are more anonymous when the anonymity set contains more people, right? So if I know that 1 out of 2 people were the ones sending me a message, then that might not be very anonymous, because, well, I mean, I might not be sure which of the 2, but that's such a small anonymity set that I wouldn't say that the sender of the message is terribly anonymous. I mean, I would say they have maybe deniability, that I didn't do it, it was the other guy. But that's a very small anonymity set. If, on the contrary, we have an anonymity set with 2 million people, then, well, then I probably have no idea who sent me the message, okay? And it's not only about the amount of people in the set, it's also whether some people are standing out as being more likely than others. So the more everybody in the set looks the same, and if this is a very big set, then you have a very, very strong anonymity. I want to make a note about anonymity layers. So here I'm talking about network anonymity. So the names that we are trying to conceal are IP addresses. In this picture, Alice is contacting Bob, and she's appearing to have a different IP address when she arrives to Bob, because that's how she conceals her true name, which is her true IP address. Now, the communication layer is just one part of the system. Alice might be using a very nice anonymous communication system that fully conceals her IP address from Bob, but still reveal her identity at other layers of the protocol. So for example, she might have a cookie that she sends to Bob that contains an identifier that enables Bob to know who Alice is, or maybe she's filling a form, providing her name and an address and whatever, or maybe she's digitally signing something with a certificate that is linked to some hard identifier, or using a payment system such as Visa that is also identifiable. So in those cases, no matter how good the anonymity is at one of the layers, it will be undermined by information leakage in other layers. And if we look at the full picture, and here I just put some layers that where identifiers might be exploited. I mean, it goes from the lowest physical layer, where your mobile phone or device might have a radio fingerprint that is distinctive, such that whenever this device is detected, I can identify that this is the device that I saw yesterday, the device that belongs to a certain person. Then there is the network identifiers and metadata, which is what we are mainly discussing in this talk. And then on top of that, you can have like the fingerprints for the device or for the software installing the device. Like browser fingerprinting, for example, has received a lot of attention, where you're able to identify or re-identify users based on who delete cookies, based on recognizing their configuration, the configuration of their browser and device when they come back to your site. Anything that involves persistent behavior or persistent identifiers can be exploited for linkability and therefore de-anonymization, and even things like writing style. I mean, you might be publishing a text through a fantastic anonymity network, but if you have an extremely distinctive writing style, that might be used to identify you. So the lesson here is that leakage that enables the anonymization can occur at multiple layers. And when you're designing a system, you need to be careful to see that you are not undermining all the effort that you're putting at a certain layer by having a leakage of identifiers at a different layer. And when we model anonymous communication systems, because of this idea of anonymity sets, we need to have a different model in mind, that when we just look at confidentiality, integrity, authentication in the classical secure communication model, in the sense that normally we will just have, Alice and Bob. Alice is sending a message to Bob, and Eve is the adversary who's in between Alice and Bob with access to the communication line between them. And then Eve will try to do things to this message to either find the content and break the confidentiality, or modify it without Bob realizing and breaking the integrity and so on. But in this classical secure communication model, we cannot really model anonymity, because here it starts with the point that Alice sends a message to Bob and Eve is able to see that. So that's already kind of broken by design. So just to emphasize this thinking in sets, when you're thinking of anonymous communication systems, what you have is not an Alice and a Bob, but rather a set of Alices and a set of Bobs, and this can be the same set, Alices and Bobs. You can have a system in which senders and receivers are taken from the same population. And then you have to specify what is the visibility of the adversary. Sometimes in some systems are designed for adversaries that are only able to see Alice's communication, but don't have access to the network beyond that, or only Bob's communication, or only some parts of the network. Or we can have adversaries that can see all communication links as well. So if we want to think beyond anonymity, what would a perfectly private communication network offer? Is anonymity the only thing? And you will see that there are many different properties we might want to desire here, right? So ideally, we would want Alice to be able to communicate, preventing adversaries from learning what she's saying. So this is the easy part. We use end-to-end encryption. who she's communicating with, sending or receiving messages. So this is the anonymity that I was talking until now. But we can go further and say maybe we don't want to reveal when she's communicating, or how long she's communicating, or from where, or how many bytes she's sending or receiving, or any other distinctive patterns that might enable inference on private attributes from Alice, or even whether she's communicating at all, yeah. So if we want to translate this into privacy properties, just to formalize things a little bit more, we have, okay, confidentiality of content, anonymity, and anonymity, we can split it into different properties, because once we start opening the box of anonymity, it's actually more complicated than it seems. So we might want to have sender anonymity. So that means that I am able, in a system that provides me with sender anonymity, I am able to contact a receiver and send a message to a receiver, and the receiver doesn't know who sent this message. We might want to have also receiver anonymity. So this is a lot more complicated. This means that I am not only able to send you a message without you knowing who I am, but you are also able to reply to me without knowing who I am. Either reply to me or even reach me without knowing what my IP address is. So this is a little bit similar to hidden services, onion services in Tor, that you're able to contact the service without knowing the address of the service, right? So this is actually much more complicated to achieve than sender anonymity, that's simple sender anonymity. And then the easier property is when you have anonymity when your interest is to have anonymity towards third parties. So there are applications where you're not so much interested in being anonymous towards your correspondence. So for example, when I send emails, I normally, sign them, and I normally want the other person to know that the email comes from me. Same for instant messaging, for example. I don't want to just send messages to people and they are not able to determine who I am. I want them to know who I am. But I might not want anybody else, any other third parties, to be able to tell that we are communicating with each other. So there are many use cases that require this third-party anonymity, which is actually the easiest of the three to achieve. Now, beyond anonymity, there is also the concept of unlinkability. So unlinkability is actually establishing that if I have two messages, two actions, two pieces of information, two records, that I am not able to determine that they are related to the same user. Okay, so for example, if we want to have a system with sender anonymity that also provides unlinkability, that means that when I send you two messages, it's not only that you don't know who they come from, but you're not able to determine whether the two messages were sent by the same person or by different people. Alternatively, you could have a system that has sender anonymity, so you don't know who the sender of those two messages is, but you know that the two messages were sent by the same user. Now, the issue is when you have a lot of linkability, there's a relationship between unlinkability and anonymity. And when you have a lot of linkability, so for example, that all my messages can be linked together as coming from me, even if you don't know who I am, the thing is that you're able to start building a kind of dossier on this anonymous user. And especially if each additional message is giving you more insight into who this person might be. So now this is a person that is interested, I don't know, in privacy, and that is interested in Leuven, and that is interested in, I don't know, a bunch of other things. Then you might start narrowing down who this anonymous user might be. So linkability is normally thought of as undermining anonymity. Now, beyond a stronger property than anonymity and unlinkability is what is called unobservability. So unobservability is about concealing your usage of the system. So when you're using it and how much you're using it, what's the volume of messages that you're sending and receiving. Of course, to achieve this kind of property, we need to use what is called dummy traffic, and I will come back to dummy traffic later. Which is basically that people appear to be active in the system by sending messages, but these messages are actually meaningless. They are automatically generated and they are not related to any user action. So that's the basic technique to provide this unobservability, so that you're not able to tell. You see a message being sent, but you cannot tell whether this is the user doing something or whether this is automatically generated. So that gives you, obfuscates effectively your view on when this person is sending and how much they are sending or receiving. And then undetectability is about concealing participation in the network. So this is extremely hard, actually. Depends on your threat model. If you have very strong threat model, it's very difficult to achieve. But of course, this is also an important property, particularly more related to censorship resistance. If you are in a place where there is censorship in your access to the participation in the anonymity network, then you might want to be able to participate without this participation being available to an adversary. Okay, there are a couple more properties that are important, even if they are not strictly kind of in the same family as the previous ones. One is distribution of trust. So mixed networks and anonymous communication systems in general are distributed systems in the sense that you don't want to have a central point of failure that is able to correlate, is able to know all this private information that we are trying to protect. So what mixed networks and similar anonymous communication systems do is that your communications are relayed via various intermediaries, such that it's enough for some of those intermediaries to be honest for you to get some privacy. In the case of mixed nets, it's typically the case that it's enough for you to go through one honest mix in order to already get some level of protection. And then another important property is forward security to limit the impact of participant compromise. As we will see in some of the later slides, in mixed nets, we need to use, we don't have the capability of using ephemeral session secrets like onion routing, which I believe you heard about earlier in the week, because they are not interactive channels. It's more of you send a message and then the message is processed in the different hops. So that means that you need to use public key cryptography, and that means that if one of the intermediaries is corrupted, they might be able to decrypt previous communications. So to prevent that, you need to kind of update keys periodically in order to ensure that there is forward, that compromise compromise of a node doesn't necessarily compromise previous communications or limit how much towards the past the adversary can go. So this is kind of a high level intuition of these properties. Now there's been quite some work in the last years looking into privacy properties in anonymous communication systems. The latest work is from last year, from 2019. It was presented in PETS. And it's on privacy notions on anonymous communication systems. They identify 28 notions, and they basically create a series of indistinguishability games, depending on what is the power of the adversary, so what is the capability of the adversary, and what is the specific relation or specific metadata that you want to hide. So as you can see, it can become quite complicated. This one of the nice things about this study on privacy notions is that they also look at a hierarchy. So which notions imply others, which are strictly stronger than others. So this is kind of the summary of these properties. So you can see, as you can see, if you are designing an anonymous communication system, and if you want to make a very kind of formal claims about the kind of privacy that it provides, and that can be, sender anonymity, receiver anonymity, unlinkability between senders and receivers, and observability, and so on, then you need to be very specific into what is the game that you are kind of playing with the adversary in order to ensure that the adversary cannot obtain the information of interest. Okay, so talking about adversaries, mixed nets are designed to resist what is called powerful network adversaries. This is different from onion routing, actually. So what are these powerful, what are these powerful network adversaries? In terms of capabilities, it is usually assumed that they can monitor all links in the network. So this is a pretty powerful threat model. You can see all the links. Interestingly, if you want to consider weaker threat models, then you run into problems when evaluating anonymity with some of the methods, because you don't have complete information. This adversary is not able to know, for example, how many people there are in an anonymity set. So usually considering global network adversaries, meaning that they can see all links, is not only giving you a sense of what is the worst case scenario if you have this kind of adversary, but also enables you to see to what extent the leakage in the network can be exploited and to what extent you are protecting, the techniques that you're using are protecting the metadata. So in addition to monitoring all the links, it is assumed that the adversary can compromise some of the entities in the network, for example, by injecting his own nodes in a sort of civil attack, or maybe not injecting his own nodes, but compromising existing nodes, either hacking into them or coercing the operator. And this is why it is important to have forward security and deniability, so that, once the operator is compromised, the node operator is compromised, this is not compromising prior communications. And then often the adversary can have active capabilities, meaning that the adversary can inject messages, delete messages, modify messages, and so on. In terms of objective, of course, it depends on what is the anonymity notion that you're kind of focusing on. Typically, the main objective in an anonymity network will be to determine who communicates with whom. But as you saw in the slide with all the privacy notions, this objective can be refined substantially. And also you might have different objectives. So, for example, determine whether Alice is sending messages or not, right? So that typically who communicates with whom will be the main objective of the adversary. In terms of limitations, the adversary cannot break cryptographic primitives or see inside the nodes it cannot control. So this is kind of the crypto ensures that you don't have to worry about content. And then the fact that the adversary cannot see inside the nodes it does not control is what gives you, is kind of part of the trust model, right? So that you trust that those nodes will act honestly, follow the protocol, and not leak to the adversary their internal state. Of course, if everything is corrupted, if all the intermediaries are corrupted, then, well, there's nothing you can do, actually. Then it's game over. And in terms of methods, the adversary collects this metadata, collects the timings when messages are going from one place to another. Typically, these messages will be routed through multiple intermediaries. So the adversary is basically looking at when somebody receives, when they send. They know the internal workings of each of the components. So they know, for example, the distribution of latency of messages in each of the intermediaries. And they use all of that information to analyze the metadata and then come up with inferences about the information of interest, such as, for example, which might be the correspondence of Alice. Okay, and then when we want to, in anonymity systems, when we want to evaluate how successful is the adversary or how good our system is in protecting, providing anonymity and other privacy properties, we need metrics. So a number of approaches have been proposed in the last 20 years. The oldest approach is what is called possibilistic metrics. So this is basically saying the anonymity set is all the people who might possibly be the person, the target, the person of interest, right? The anonymous user. So if anybody who might be in that set is part of the anonymity set. Now, this is not, it's a bit too coarse. Of course, it gives a first idea of how anonymous you might be, but it's a bit too coarse. So additional or more elaborate metrics, they consider not only who is in the anonymity set, but how likely each of these individuals is to be the sender of the message. So for example, here, let's say that we have 4 users that are possibly the sender of this anonymous message. And because of when they sent messages, because of the observations that the adversary made in the network, It might be that there is some of them appear as more likely than others. So in this case, user 4 appears as the most likely user, while user 3 appears as the least likely user. So in this case, it's not just about how many people there are there, but we need to take into account as well how uneven or even is this distribution, because it's not the same to have an anonymity set of 1 million people where they are all equally likely to be your targets, compared to a system where you also have 1 million people, but with 99.9% probability, it was actually Alice. And there's like a very negligible probability that it was somebody else. The anonymity is not the same in both cases, because in one, you have a lot more confidence in who might be this anonymous user, while in the other, you have a lot of uncertainty about the identity of that anonymous user. So in that sense, one of the ways to express how anonymous people are, what is the size of the effective size of this anonymity set, is to use entropy. You have the formula there of the entropy, which basically takes this probability distribution and checks how many bits of uncertainty we have. Now, one of the nice things of entropy metrics is that they capture scalability. So they capture both this uniformity or skewness of your distribution among the anonymity set, as well as the number of elements, subjects in your anonymity set. A different approach, a more modern approach, is to look into indistinguishability and to use concepts close to those of differential privacy. So here you can formalize anonymity as a game where, for example, you have two users, 0 and 1, each of them send a message, and the game is such that one of them is sending the message to receiver R, and the other is sending the message to some other random receiver. And the adversary knows that the message received by R must come from either 0 or 1, and then performs an analysis and derives the probability that the sender is 0 or that the sender is 1. Then once we have these two probabilities, we can look at the differential between them, the ratio between them, and compute an epsilon that is similar to the differential privacy epsilon. And this gives us how much more likely is 0 to be the actual sender compared to 1. So these metrics, they capture how close to perfect is the system, right? So if you have epsilon 0, that means that the probability that it was 0 or 1 is the same, and you have a perfect system. So in my opinion, I see the entropy and the indistinguishability metrics as being kind of complementary, in the sense that with indistinguishability alone, you get this sense of how good is your system compared to perfect. Perfect is, of course, epsilon equals 0, meaning that they are completely indistinguishable. But this indistinguishability metric does not scale, in the sense that if I have a system with two users, that is a perfect system, I will get epsilon equals 0, which says, okay, this system is as good as it can be, you know, you're perfect to go here. But actually, if the system is designed in a way that is for two users, this is kind of really bad. And this will not be expressed in this epsilon. This epsilon will not capture that. On the other hand, with entropy metrics, it's a bit the other way around. We get a sense of how big is the anonymity set, the effective anonymity set. So with anonymity metrics, if for example, if you do the analysis and you say, okay, so the sender of this message, we have an entropy of 10 bits. So that means that we have roughly like 1,000 people that are equally likely to be the sender of the message. Okay, that gives us a sense of how anonymous we are. It's like I am indistinguishable in a group of 1,000 people. But that doesn't tell me how good is the system compared to the best that it could be. It's not the same to have 10 bits of anonymity, which is indistinguishability in 1,000, when you have 1 million people in the system than when you have 2,000, right? So one of them kind of tells you how big is the set, and the other tells you how close to fully indistinguishable is the system. So I think that if you're evaluating anonymity systems, you probably want to use both in order to get a sense of both in both ways. Okay, so let's move on to mixes. which are the basic building block of anonymous communication systems. The oldest proposal is what is called the Chaumian mix. Chaum proposed it already in the early 80s. And the mix is, in this original proposal, is a proxy for anonymous email, okay? So the goal of this system is that it's a router that the adversary can observe all the inputs and outputs of this router. And even with all this information of all the messages coming in and out, it should not be possible for the adversary to determine which input corresponds to which output, okay? So it should be basically unlinkability between inputs and outputs. So the way that this is achieved in Chaumian mixes is through a shuffle. So basically, the router will collect a certain number of messages. In this example, in the slide is 4. I mean, normally you would have a much higher threshold. It takes on these messages until this number. And once the full number has been received, it will cryptographically transform these messages and then send them out. So the cryptographic transformation achieves what we call bitwise unlinkability, which means that it is not possible to relate the input to the output based on the message content, based on any headers or payloads or anything. So the message has been completely transformed and you have no idea which input corresponds to which output. Of course, constant length, fixed size is important here because otherwise you would be able to correlate based on size. That's the easy part, actually, the bitwise unlinkability part. The more challenging part is to prevent traffic analysis that is based on message ordering, right? The way Chaumian mixes achieve that is by batching. So basically, no matter when these inputs 1, 2, 3, 4 are received, the mix will not send anything until all of them are received, and then it will send them out in a randomized order. So output 1 is equally likely to be any of the 4 inputs, actually. Okay. And already in the original proposal from Chaum, it already says, okay, we shouldn't have just one of these routers because then it becomes a central point of failure. So that's not, you just move the trust to this router, which is not so great. So let's have a sequence of routers, and then let's pass the mix through all these pass the message through all these intermediaries, such that it's enough for one of them to be honest for us to achieve the desired anonymity properties. There's been many alternatives to Chaumian mixes. Time mixes was one of them. So the problem with one of the problems with Chaumian mixes is that the mix only sends messages once it has received the threshold number, and with the threshold being a parameter, right? So if you have very low traffic in the system, what could happen is that messages are delayed a lot. You have no guarantee effectively on when the message will be delivered, because you're depending on how many other messages are getting to that mix until it hits the threshold and kind of shuffles and sends the messages onwards. So time mixes, what they do is that they flash periodically, say every whatever 5 minutes or every whatever time out, regardless of how many messages have arrived. Now, of course, the problem here, if you do that, is that you might be in a situation where one message arrives, only one message arrives, or a very small number of messages arrive, and then it's sent out, and then you get no anonymity because the anonymity set is very small, because you don't have many messages to be confused with. So you can have to address that optional flashing conditions, such as, for example, you send messages out every 5 minutes, but only if you have at least, whatever, 50 messages, right? You can have conditions. Now, a more interesting variant is what is called pool mixes, and this was already introduced in the late 90s. It was implemented in Mixmaster, which is one of the early implementations of remailers, mixnets for anonymous email. And in a pool mix, the idea is that you have kind of an internal memory that you keep in between rounds, each round being a kind of a sequence of receiving messages, shuffling them, and sending them out, right? So the idea in pool mixes is that you would have, in this case, if you see the figure on the right, this is a mix with threshold 6 and pool 2. That means that it flashes when it receives 4 messages, and it keeps 2 messages in between rounds. So in this case, we would have 2 messages in the mix from the previous round, then 4 new messages arrive, and now 4 random messages are sent out. So one of the really nice things about pool mixes is that they make anonymity sets much stronger, in the sense that in Chaumian mixes, you have n inputs, n outputs, and your anonymity set is totally given by that n, right? You have those options, that's the full anonymity set. On the other hand, in pool mixes, once your message goes in, it might go out in the first time it flashes, in the second, in the third. So with asymptotically lower probability, it might be flashed in any of the subsequent rounds. So that means that the anonymity set is for a message that comes in, actually theoretically includes all the future messages that come out of that mix. I mean, in practice, at some point, the probability becomes really, really tiny. But in a way, this design with pool mixes, it provides you with much better anonymity than Chaumian mixes. Now, on the downside of pool mixes is that they increase the variance of latency, in the sense that it might be the case that a message is not chosen to be sent for multiple rounds, and that the end-to-end latency of that message is actually very long. This is pointing actually to a well-known trade-off between anonymity and latency, in the sense that if you have a certain amount of messages coming into your system, and you want to increase the anonymity set of those messages, you will have to increase the latency, because you will have to make it possible for each input to be more outputs, and that means that it is actually delayed longer, so that there are more possible messages with which it can be confused. So this is a well-known trade-off, that if you want more anonymity, you might have to introduce more latency for a given traffic load. And then there's a different type of design based on a different principle that is not shuffles, which is continuous time mixes. These were proposed first in '98 by Kesdogan with the name Stop and Go, and were proposed again as Poisson mixes more recently in the Lupix design. And the concept here is that instead of collecting a number of messages, batching them, shuffling them, and sending them on, here each message has is delayed individually, and the delay that is applied to the message is drawn from an exponential distribution. Okay, so these mixes actually function like a queuing system, like an infinity system. So basically that means that we assume that the arrivals are distributed exponentially, and then the service time is exponential, because this is the latency that is applied to the message. What is interesting about this, and is special about the exponential distribution, is the memoryless property, right? So actually, anonymity in continuous time mixes is computed very similarly to that of pool mixes, in the sense that if we have 2 messages coming at T1 and T2, and then one message then leaving at T3, even if message 1 arrived earlier than message 2, and both messages have a delay that is picked from an exponential distribution, it turns out that the probability that the message being sent out at T3 is the first or the second is actually the same. This is because of the memoryless property, that once the first message did not leave after A time units elapsed, then the first message to come out is equally likely to be either of the two. And another interesting thing about continuous time mixes is that the delays are actually picked by the sender of the message. So contrary to threshold, or Chaumian, or pool mix designs, where you have no idea when your message will be delivered because it depends on how many other messages arrive and when it's chosen to be sent onwards to the next destination. Here you specify how long it should dwell in each of the intermediaries so you can predict the delivery time. I mean, of course, with some noise because you might not have perfectly accurate estimations for the propagation time in the network, but you do know how long it will be staying in each of the intermediaries, and that gives you a good estimate on when it will be delivered. Okay, so these are the basic building blocks, but now how do we put them together in networks? As I said before, it is very important to distribute trust, to avoid single points of failure. So the way we achieve that is by routing messages through multiple mixes, such that even if some of them are malicious and actually leak to the adversary the correspondence between inputs and outputs, we're still achieving end-to-end anonymity. So once we move from the basic building block into networks, there is many issues we need to consider. What is the network topology, for example? Is it possible to pick, if we have a set of nodes of mixes, is any sequence of mixes allowed in this system, or do we have some constraints in the routing that, for example, we choose certain mixes to be, you know, in the first hop and certain others in the second hop and so on. Who selects the routes? There are two big families of systems. This is what is called source routed and hop by hop routing. In source routing, the sender of the message is the one determining the full path, the full sequence of hops of intermediaries all the way to the destination, while in other systems, the routing is done on a hop by hop basis, meaning that the sender sends it to some node in the network and then that node decides where to send it next. Of course, with source routing, the sender has much more control over the full route. The disadvantage is that you need to know the full network. You need to be able to encrypt for each of these intermediaries. So that might, in big networks, that might be a lot of overhead. On the other hand, in hop by hop routing, the disadvantage is that if your successor is compromised, then you might select compromised nodes from then onwards, doing what is called a root capture. So it's actually more difficult to secure and provide anonymity guarantees to systems that use hop by hop routing, even if they are more efficient, because you don't need to know, you just need to know one entity to get your message into the network. And then there is a lot of features that you need to consider in order to get to some point in the trade-off between latency, anonymity, and bandwidth. So this is what is called the anonymity trilemma, and it is well known. I already mentioned that anonymity is traded with latency. The third kind of element in this trade-off is bandwidth. I said you trade anonymity with latency when you have some sort of a level of traffic flow. Of course, when you have more traffic, then it is possible to have the same anonymity with lower latency. So you have to play basically with these three corners of the triangle. You can easily have two, but you cannot have the three. So you can have a system that is very low latency and has very little overhead in terms of bandwidth, but then you will have very little anonymity as well. You cannot have high anonymity with little traffic and low latency. On the other hand, if you're willing to have, like, you have a system that is very latency tolerant, then even if you have low bandwidth, you might have good levels of anonymity. And the other way around, if you want to have low latency and high anonymity, one way to achieve it is to have a larger user base or to have a larger traffic flow by using, for example, dummy traffic. But yeah, these are, you have to choose, you have to make trade-offs on where in the design space you want to be. What is more important to you and your application? Is it latency? Is it bandwidth? Is it anonymity? So we did a study on anonymous. This was a systematization of knowledge paper, and we looked into a number of features that are important when designing and analyzing anonymity systems. So this includes the network topology. So how connective is the network? Is the network fully connected? Is it only partially connected? In terms of connection type, are the channels unidirectional or bidirectional? and is communication synchronous or asynchronous? So with synchronous, asynchronous, I think that's an important one, because the systems that require synchronous communication, I think they are very impractical, in the sense that there are some proposals that offer some anonymity guarantees, but only when the user base is very stable. So nobody's leaving, nobody's joining, and everybody is sending exactly one message per round, and nobody's ever offline. And otherwise, if you start relaxing those assumptions, then the guarantees don't hold. And I think that's very impractical, because, yeah, unless you're in a highly structured environment, like having this guarantee that everybody will be always online and will be sending at the same time and so on is actually not so easy to achieve. Then in terms of symmetry, there is a kind of, we can have systems that are very symmetric, in the sense that all the nodes have the same functions, all the participants have the same functions. They all, for example, send and receive messages and mix messages for other users. So that would be like a purely peer-to-peer system. There have been a number of proposals on peer-to-peer anonymity, but none of them has been very successful or very convincing. It's very difficult to achieve. The more kind of solid designs that we have are more client-server, where you have like users that communicate with each other, and then you have these mixes in this that form the kind of the network infrastructure that are serving those users by doing the mixing. Then in terms of routing, they can be flat or hierarchical. Most systems that I know of are flat. And then in terms of decentralization, even if mixed networks are typically decentralized systems, it is not uncommon to have semi-centralized components for functions such as directory service. So for example, I mean, Tor is not a mixnet, but it's an anonymous communication system. And for example, in Tor, they have authorities for the directory server. So this is the entities, the servers that will tell you who is part of the network, and will tell you the keys and addresses of all the nodes that form part of the network. And you need this information in order to prepare your packets and route them through this network. So of course, if they are malicious and they give you on the adversarial nodes, then that is a major problem. Another issue is another type of authority that is often semi-centralized, or is measurement authorities that kind of check whether what's the available bandwidth of mixes and whether they are routing packets or not. So that's also non-trivial to solve in a decentralized manner. Routing information. So, okay, so somebody is routing packets through this network. What do they need to know? Do they need to have a full view of the network, or is it enough to just know a subset of the nodes in the network? So most designs require complete knowledge, which is a problem if you want to scale up, because if you have a very large network and you need to know all these keys and addresses for nodes, and you might have some churn, some nodes joining and leaving, you might have keys being updated for forward security. So that can be a lot of overhead to just keep this information up to date locally. There is a very interesting proposal, Walking Onions, that is for Tor, that kind of relaxes, allows to achieve the same kind of security without having to download and keep up to date a full network view. So that's very interesting. And then how is this information updated? Is it event-based? When somebody joins or leaves, you update it? Or is it like periodically? Tor, for example, is periodic. Every 2-3 hours, I think they publish a new consensus document. In terms of routing, who decides on the route? So I already mentioned that there is this difference between source routing and hop by hop. And source routing is the sender, the original sender, who chooses the full route, while in hop by hop, each intermediary decides on the next destination. Is the traffic all treated the same, or do you have some prioritization? Prioritization is in general considered quite dangerous, because it allows you to possibly partition anonymity sets. So this is usually not desirable if you want to have really good indistinguishability, that all the traffic looks the same to intermediaries. And then how do you select these nodes? Do you have a deterministic or non-deterministic algorithm? Usually it is non-deterministic, so it's randomized. And do you have some constraints on who you can choose? So sometimes you can choose any combination. Sometimes you have restrictions that have to do with security. So for example, in Tor, you are not allowed to choose two nodes that come from the same IP subnet. Or it can be, you can have constraints that try to optimize end-to-end latency or performance. Or maybe you can have constraints that are based on user trust in different nodes, right? And then how is this probability? You know, is it weight? Is it uniform? Is the weights, are they dynamic? Are they static? If they are dynamic, what do they depend on? Do they depend on, like, for example, available traffic or some performance measure of the nodes and so on? In terms of latency, the systems can be low latency, like onion routing, that does not apply any delay to the packets it routes, or higher latency, like mixnets. And of course, within the mixnets, you can have, you know, systems that are very high latency, or systems that have more constraints. If you have, for example, time mixes or continuous time mixes, you can set that latency to be within bounds, so that it's still low enough to serve the application of interest. And then a very big distinction is between connection-based and message-based. Connection-based is systems such as onion routing, where the anonymous routing means that you establish a connection from yourself to your destination, and that's like a session that is a bidirectional channel that you can use throughout the session, and then it becomes destroyed at the end of the session. And that's in contrast to message-based, where each message is routed independently. And of course, that means that each message has to have the full routing information. It's not enough to just say this message belongs to a circuit, and then the nodes know, you know, what to do, where that circuit is going, and which keys to apply to it. And then, yeah, we looked into whether the systems were implemented or the code was available. So maybe just to, because this was a lot of features. So maybe to zoom out and to look at some of the most important differentials between mixed networks and Tor. How are they similar and how they are different? What is similar is that they are source routed systems with nested encryption. That means that each of the intermediaries will kind of peel off a layer of encryption. This is, I mean, in mixnets, there are like some variants that don't use nested encryption. For example, there are voting mixnets that are designed for voting. They use re-randomizable cryptography in order to be able to prove that they correctly did the shuffle, meaning that they would publish all the inputs and all the outputs, and a proof that shows that the outputs are re-randomized shuffle of the inputs. And that's necessary if you need to have like very strong verifiability as is needed in voting. And what is similar is that these are overlaid networks with multiple hops, and the concept is that you don't go directly to your destination, but instead you go through all these intermediaries, and each of them is kind of redirecting your communications and helping you reach your destination, without adversaries being able to link you and your destination as talking to each other. So what is different is that Tor is connection based. So that means that you establish a circuit. So in Tor, as I guess you heard on Monday, you open this circuit with these onions, and then you can use that circuit for all the packets. So of course, that means that all the packets that go within the same circuit are linkable to each other, and all the intermediaries know that these packets are part of the same circuit, right? This is different from mixnets that are packet-based. So that means that each packet is completely independent. It doesn't belong to a circuit. And that means that it has to have full routing information in the packet, okay? And then another major difference is that Tor or onion routing in principle does not add latency to packets. This is partly because these are systems designed for very highly interactive applications, such as web browsing, that are very intolerant of latency. While in mixnets, adding latency is part of the security mechanism, part of the anonymity mechanism in order to create these anonymity sets. Right. So this latency issue introduces a very big difference in the threat model that onion routing and mixnets protect against, in the sense that if you don't have any latency, as in onion routing, you are vulnerable to what is called end-to-end confirmation attacks. Okay, so in end-to-end confirmation attacks means that if you have an adversary that is able to see my connection to the Tor network, for example, and is able to see at the same time the connection of the exit node to the final destination, it is possible to link the start, so link me to this destination by looking at the start time of the circuit, the end time of the circuit, the number of packets sent, and other features of the traffic, such as, for example, the bursts, the packets per second, and so on. Since this is not really modified, it will just be a slightly noisy version of the input, and that can be because of the variability of communication patterns that will be typically unique and will be typically possible to link source and destination. Now, you cannot do that in mixnets. Even mixnets are designed to provide you with anonymity, even if the adversary is global. That means even if the adversary is able to see your connection to the first mix and the connection from all the links in the network effectively, they are not able to say, to have an end-to-end confirmation and say, okay, this input is this output, right? What they can do is long-term intersection attack, which is a much weaker attack from the adversary's perspective, in the sense that with long-term intersection attacks, and I will come back to them towards the end of the talk, the adversary is able to infer that some recipients may be more likely than others to be the recipients of the user, but that is more like over a long period of time, I infer that maybe Alice is friends with Bob. That doesn't mean that I can determine that this message that Alice sent actually went to Bob. So it's kind of a statistical inference on the communication profile of the user, rather than a confirmation of like, okay, a communication is happening right now between Alice and Bob. So that's, in that sense, that's what you gain with adding latency, right? So yeah, that's the adversary model is different. And then in both systems, you can use dummy traffic. Onion routing systems, to my knowledge, don't use dummy traffic. While in mixed networks, dummy traffic schemes have been proposed. And basically dummy traffic, I will also speak a little bit about it, is fake messages that are added to the system to strengthen anonymity and enable unobservability. They enable unobservability because if I don't know whether you're sending something yourself or whether your computer is doing something while you are, taking a nap, then I am not able to infer things about your activity. So if you want to route things through multiple mixes, you need some sort of packet format that enables you to do that. The kind of standard is Sphinx that was proposed already in 2009 by Danesis and Goldberg. The Sphinx packet format is a compact packet format for nested encryption. And what is similar to onion routing is that each mix in the path, each intermediary in the path peels off a layer of encryption. Now, there's a big difference with onion routing because, as I said, there is no interactive circuit session establishment. Like in onion routing, you can do a Diffie-Hellman exchange and derive a secret key, a shared key for the session that then is used to encrypt all the packets going in that circuit. Here, it is not possible, so the keys must be derived from the packet itself, right? So the way this works is that the sender introduces a group element in the beginning of the packet, and each of the mixes can combine these group elements with their private key in order to derive a shared secret that they can use to decrypt the routing information and verify the integrity of the packet. They also have to blind this group element before passing it on to the next hop, as otherwise the group element would be an identifier that stays constant as the packet travels, which would break the bitwise unlinkability. So this offers per hop bitwise unlinkability in the sense that when you see two incoming Sphinx packets and two outgoing Sphinx packets, you have no idea which input corresponds to which output unless you have the private key of the mix. It also has tagging attack detection. So tagging attacks, as you know, are attacks where adversaries may modify, this is for the header specifically, may modify some bit in the header in order to detect downstream when a mix receives a packet with corrupted header information, right? So that would enable an adversary to do some tracking attacks. And what Sphinx does is that it has this tagging attack detection, which is basically that if you have this integrity tag, that if any bit is modified in the header, then the integrity tag will not compute. So it's a kind of all or nothing scheme. So if the adversary modifies any bits, then the next receiver will, the integrity check will fail and the message will be discarded rather than be further processed and possibly be used in some form of attack. And it also has replay attack detection. So one of the problems, one of the possible attacks would be that I see you sending a Sphinx packet to a mixnet, and I could take this Sphinx packet and then send it over and over and over and over and over and over again. And every time I send it, I see, what is happening in the network, who is receiving in that network. And over time, if I keep sending the same packet over and over again, the pattern of who's the receiver will always appear every time I replay this packet. So this would be a problem, right? So the way Sphinx deals with this is that it takes these group elements and it keeps a record of it. And then if a new message comes with the same group element, it is considered a duplicate and discarded. And this list of group elements can be forgotten once you do an update of the mixed key. So when you do the key updates for forward security, you can also forget about this seen group elements. There's a trade-off there as well, in the sense that if you have a very fast updates of keys, then it's good because you will have short lists that you have to check for replay. And it's good because compromise will give an adversary very little insight into past communications because the key will not be going back very much. Of course, it comes with downsides, which is that you might have obsolescence of messages that arrive to a mix when the key has already been updated, and therefore it's no longer, the message is no longer valid. And also overhead in this downloading, especially in source routing systems, which is what, Sphinx is for source routing anonymous communications, that you have to have up-to-date keys. So if you have a very large network with many mixes and the keys are changing very fast, then you need a lot of overhead to be downloading all these keys. Okay. So another feature of Sphinx packets is what is called SERPs. So this stands for single-use reply blocks. And what they basically are is Sphinx headers that route back to the original sender, and they are prepared by the sender. So if I want you to send me back a message and I don't want to reveal to you my IP address, I can give you a SERP, and the SERP will contain is basically a set of headers that will, when sent to the mixnet, route back to me. But because this is my address is actually buried buried under all these nested encryptions, you are actually not able to see what my address is, right? The reason why it has to be single use is to prevent replay attacks. If you have like some of the early designs of like Mixmaster, Cypherpunk remailers, second version, type 2, they had replies. So they had some scheme for replies, but of course, if the replies can be used infinitely, then I would be able to find you, because if I have capability to look at the network, because I will do what I said before, right? Send the message over and over and over and over again until you are the only one who's always receiving whenever I send, and the other people are changing, right? So what can you use SERPs for? You can use them for indistinguishable replies. So when a mix is processing a SERP, it cannot tell that this is actually a SERP rather than a normal forward message. So they look exactly the same. You can use them to implement reliable transport. So most mixnets do not implement reliable transport, but you can use SERPs to implement it. So basically, if I send you a message, I can include a SERP in the payload, And then you can use this SERP to send me back an acknowledgement once you have received the message. And they can function similarly to onion addresses in the sense that I could publish SERPs to reach me together with some maybe logical identifier. I'm like, you know, some pseudonym in some system that is completely meaningless. But if you want to contact that pseudonym, here are some SERPs that you can use and the message will get to me. There are some practical challenges with SERPs. The limited validity. So this is a trade-off with forward security in the sense that because the sender has to prepare them in advance, it has to use keys that will still be valid when the receiver is sending this back, right? So if you have very fast updates of keys, then you can run into problems that the SERPs become invalid too quickly, right? And then the other issue is that if you want to have SERPs for receiving, anonymously receiving data, and you have an application where the downstream traffic is much larger than the upstream, then this is also a challenge because I would have to basically send you a lot of messages that are packed with SERPs in the payload so that then you can, you know, use each one of those to send me back downstream traffic. Okay, and dummy traffic, as I mentioned, are fake messages that can be introduced to make it harder for the adversary to figure out what's going on, who is sending and when they are sending and to whom they are sending. Dummy messages have to be indistinguishable from real traffic, otherwise they don't fulfill their function. So any intermediary that is processing a dummy message should not know that this is a dummy message. They increase anonymity because they increase volume. So as I said, there is this trilemma between anonymity, latency, and bandwidth. If you increase the bandwidth, then you have better anonymity for the same latency, right? So they are good for anonymity, and then they allow you to have an observability in the sense that now it's not clear that you're doing something because seeing you send a message is not as informative as it might be that you are not doing anything at all, and it's just your computer sending a dummy message. When you're designing the dummy traffic strategy, there are many things you might want to take into account. Are these dummy messages generated by users or by mixes? And you might want to have both. If you don't have dummy traffic generated by users, then you might not cover like the kind of the first and last legs of the system. So yeah, that's it's desirable to have users involved in the dummy traffic generation. And mixes also have a good view on how much traffic is currently being routed in the network, and they can also adjust their dummy traffic generation to ensure, for example, that a minimum anonymity level is achieved because there is a minimum amount of traffic flow in the system. Was the destination, because the dummy traffic, intermediaries will not be able to see that this is a dummy message, but it has to have some final destination, and the final destination will be able to check that this is actually a fake message that can just be deleted rather than being passed on to some application. So what's the destination? It can be some intermediary mix, it can be some other end user, it can be yourself. There are arguments why sending dummy traffic to the self is a good idea. Of course, that means that nobody else, no other party will be able to see that this is a dummy message. So that's a good thing. Only the generator, the entity generating the message is able to at the end discard it. So that's great. And also having messages come back to yourself, you can use that to get a sense of the health of the network. So for example, if you're generating dummy traffic that routes back to yourself and you see that you're not getting back messages, that can be indicative of a denial of service attack on the network, or maybe that the servers are down, or that for some reason things are being delayed beyond what they should. So yeah, choosing self as destination is probably the best idea. And then how frequently do you generate them, with what distribution? Do you do it dependent or independent of real traffic? So if you want to do it independent of real traffic, then that means that yeah, the generation of dummy traffic is not related to your actual real activities. That can be good or can be bad. Sometimes you might want to have dependent strategies such that when I'm actually sending real traffic, I am not generating any dummy traffic, and I only generate dummy traffic when my real activity is low, so that from the outside, it always looks as more or less the same level of activity. So there are many choices there that, depending on your constraints and your objectives, you might want to consider. And I mean, it's a difficult problem in the sense that even if you are accounting for all these features in your dummy generation strategy such that they are leaking minimal information to the adversary, that they are maximally indistinguishable from real messages, you might still have higher order correlations that are different in real and dummy messages. If you think, for example, of instant messaging, if I have an instant messaging system that is going through a mixnet, and I'm having dummy traffic that is sent, let's say, randomly every hour or so, then the pattern of communication with dummy traffic will be very different from a real conversation where I am sending messages kind of with a time between them that is not so long, and then I'm receiving in between and then sending again. And this is not the pattern that is observed when I'm idle and use dummy traffic. So if you want to make it really indistinguishable, there's a lot that you need to account for to have a statistical indistinguishability. Okay, so moving to a couple of attacks, a couple of main attacks on mixnets. So the first is what is called the blending or N-1 attack. The idea is pretty simple. Basically, this is an active adversary that wants to fully de-anonymize a message and is attacking one mix or one mix at a time. So the first thing the adversary does is to empty the mix of legitimate messages. If we're thinking of a Chaumian mix, this is very easy in the sense that right after flushing, we know that the mix is empty of whatever it had before. Then the adversary allows the target to get into the mix. In this case, the target is the green message. And then the adversary has to prevent other legitimate messages from getting into the mix. So the adversary has to have kind of the capability to either delay or delete messages in the network before they get to the mix, which is a rather powerful adversary. And then also the ability to generate its own messages, which is a lot less complicated, I would say. So now, basically, it's quite simple. What happens, this mix is receiving 4 messages and is outputting 4 messages. In principle, it is not possible to know which input corresponds to which output, but if I have generated myself 3 of the outputs and I can recognize them because I prepared those packets and then I know how they should look like after a decryption, then the one that I do not recognize is the target, right? So that basically, the mix will give you an anonymity set of n, but if n-1 are adversaries, then your anonymity set is actually 1, which means no anonymity whatsoever. This is extremely simple for Chaumian mixes. If you want to deploy this attack towards other mixes, such as pool mixes or Poisson mixes, it's a little bit more complicated, but it's also possible. And you have to do more attack steps, or it might be more difficult to make sure that the mix is empty. The thing with this attack is that it's very detectable. It's difficult to conduct it in a stealthy manner. And if you have dummy traffic that is looping back to the sender, so send to self, you would actually be able to see that the stream of dummy messages that you should be receiving from yourself is stopped, and that is indicative of a possible N-1 attack, because it means that somebody is either delaying or deleting those messages from the network. So it's very powerful, but it's expensive to conduct. It requires an adversary with very powerful capabilities, notably the deletion of legitimate messages or the delay of the legitimate messages, and it's also quite detectable. So in that sense, at least is not an attack that can be conducted easily and undetectably. The other attack is actually what is called long-term intersection attacks. This is a family of attacks. There are many variants. It relies on certain assumptions, heuristics about user behavior. And the assumption is that Alice has persistent communication relationships, okay? That she communicates repeatedly with a subset of people. And I mean, this is kind of quite reasonable in the sense that if you think of messaging or email, you don't choose your recipients randomly from all the email addresses in the world. You actually have a subset of people that you repeatedly communicate with, right? The other assumption is that we have a very large population of senders, and that when Alice is sending in each, every time Alice is sending a message, she's kind of mixing together with different people, okay? So this is, it's not that we have 100 people and in each round, each of the 100 people send exactly one message to the same receiver or to a subset of receivers, and then Alice is always with the same senders. That's not the assumption. The assumption is that every time Alice is sending, different people are sending together with her in that kind of time frame. That's a bit counterintuitive why this is important, but it is actually. So what's the method? The method is that you look at who receives when Alice sends. So you have some characteristic. I mean, this mixnet is introducing latency, but you can know what this latency distribution looks like. You can estimate it. You know that if Alice sends a message now, then the receiver will get it within the next hour, for example, if that's the characteristic. So you can see who receives in the period after Alice has sent, taking into account the kind of latency characteristic of the network. And you do that for many observations. Every time Alice sends, you record who receives, right? So the intuition is that if we observe many rounds when she sends and she's always sending to the same person or the same small group of people, her likely recipients will appear more frequently, right? So if Alice is always sending to Bob, whenever she's sending, let's assume her only friend is Bob. Whenever she's sending, Bob is receiving. And when she's not sending, maybe sometimes Bob is receiving, but much less frequently, right? So that would give you a sense that the differential between Alice is part of the sender set or Alice is not part of the sender set has an impact on whether Bob appears in the receiver set or not, right? So the result is that we can create a vector that expresses Alice's sending profile. So the result is basically a set of identities who are her likely recipients with some probabilities associated of how likely they are to be a part of the recipient sets of Alice. Some notes on this attack. This is a passive attack, so it's very difficult to detect. And it basically shows that it's very difficult to conceal persistent behavior. Like basically in an anonymity system is randomizing, you're sending a message to somebody and the system kind of introduces a lot of randomness that is noise, obfuscation, confusion for the adversary so that the adversary cannot see who's receiving. But if you keep taking the same action, the randomness, the noise is different every time. So eventually by combining many observations, the signal will start emerging from the noise because the noise kind of will cancel each other across different rounds while the signal will be persistent, right? So that's a bit the concept. And any practical anonymous communication channel will reveal long-term relationships. And by practical, I mean, to prevent this, you would need to have a system that is, for example, synchronous, in which every user sends in every round always, and they choose the receivers. It has to be super constrained to the point that it becomes quite impractical. So now this is a bit counterintuitive. So the larger the ratio between the user base and the mixed threshold, the better the attack works. So imagine you have a mixed threshold. Let's assume for simplicity that our anonymous communication system is just a Chaumian mix with a threshold 100. So it takes 100 inputs, shuffles them, outputs them, right? So if we have a user base of 100 people, with every round being basically the same people sending a message, then each additional observation will not really give us distinct information. So we will not learn much from observing repetitions or subsequent rounds. Now, imagine now that instead of that, we have a mix with a threshold 100, same as before, but now we have 1 million users, okay? So whenever Alice is sending, she's sending with 99 other people. And the assumption here is that these 99 other people will have friends or recipients that are disjoint from the 99 other people that she's sending in different rounds. So this is, again, the signal to noise ratio. In a way, the more distinct the other people are, and Alice is the only one that is permanent, the more she starts standing out, her recipient starts standing out when we look at multiple routes. So what can help with this is dummy traffic and observability, but of course, this is expensive. You have to consume bandwidth, battery, it's not so easy. And even if you have dummy traffic, you will generate dummy traffic when your application, your device is online. So online, offline status may be hard to conceal in any case. So it's difficult to have dummy traffic that is really always on in a way that is practical. Now, the good news is that long-term intersection attacks take time. So you need to have hundreds or thousands of observations in order to have some good estimation of who might be Alice's recipients. And in some cases, anonymity can be tactical. So I might not want, I might not want you to know that I'm, talking to somebody before we are taking some action, but after the action is taken, it's actually revealed that I was talking to this person. So in those cases, if your need for anonymity is tactical, then this is not such a big problem because it would take a really long time to succeed in this attack. And the other even more promising issue is that these attacks, they make a very strong assumption about user communication patterns. Typically, you would have assumptions such as, oh, Alice has 10 friends and she only sends to those 10 friends. And now, there is an attack to kind of extract who these 10 friends might be. Now, in practice, even though if I don't select my email recipients randomly, of course not, but the email recipients to whom I might be sending emails this month can be very different from the ones I was sending emails to like a year ago, right? So once you have like the hidden states, in this case, the user communication pattern, the choice of recipients, this is an evolving, this is evolving in time, that this makes it significantly harder for the adversary to infer who these recipients might be. Okay, so coming to the end, takeaway points. So one of the things that I think is very important is that anonymity needs to be protected at all layers. It's very fragile. And I think especially one of the things where this is very visible is like there's a lot of work, for example, on protocols, cryptographic protocols that have really great anonymity properties, for example, for anonymous authentication using attribute-based credentials. But even if you're doing all that great work at the kind of authentication layer, if you don't have protection at the network layer, then you're still able to kind of bypass this protection by simply looking at network identifiers. And the same happens with different layers, right? Like if you want to ensure anonymity in your application, you really have to ensure that the work you're doing at one layer is not being undermined by information leakage or identifiers that are exposed at different layers. I think a very important takeaway point is that you should really know that you cannot be anonymous on your own. So don't think of anonymity of like, oh, if I don't know the name of the user, the anonymous user, then the user is anonymous. Or if I don't give my name, I'm anonymous. This is not how it functions. You should think about anonymity as blending into a crowd. So you need to have like a crowd of users, a crowd of other peers that you blend into and who might also be the originators of the message you send. And that's what gives you anonymity. The fact that, there's all this set of people who could be the senders of the message. So anonymous routing, I mean, I guess with this monster table, you already saw that there are a lot of features that need to be selected, taken care of, and these features come with trade-offs, security, privacy trade-offs, performance, efficiency, practicality. So it's actually a rather difficult task to design such systems for practical cases. If you want to have an observability beyond anonymity, meaning that you want to conceal how much you're using the system or when you're using the system, then you will need to use dummy traffic. This is not something that you can do with simple anonymity networks that simply aggregate messages into, you know, anonymity sets. You need more than that if you need an observability. And I mean, I guess many of you are very familiar with onion routing because Tor is the most popular system. So mixnets are an alternative to onion routing. And the most important differences is that they are packet-based instead of circuit-based and higher latency. And what you gain by having this higher latency is that you can provide a stronger anonymity towards global network adversaries that, you know, onion routing systems are vulnerable against. And this is all I have. I believe we still have a few minutes for questions.
Sorry, you were saying?
So I'm trying to get now the chat.
So there is one question from Eris asking, you assume that an adversary can monitor all the links. I think it's with respect to your analysis of all the routing attacks. What if we assume that the adversary can only monitor most of the links? How much of a difference would it make in the design of protocols?
Yeah, it's a very good question. So it's a very good question that is very difficult to answer. And the problem is that if you have an adversary that can only monitor some of the links, the problem is how do you make your model for the things that you do not see? Either you have a very good prior of the distribution of the things the adversary doesn't see, such that it can say, okay, I can see most of the links and I have a prior or what might be happening in the links that I do not see. And then I can compute these probabilities of what is the likelihood of a sender receiver and what's the likelihood that I'm not seeing something and so on. But it becomes very hairy because, yeah, a lot of the probabilistic analysis that you have to do in order to see how distinguishable or indistinguishable things are, you just don't have enough information because you have these unknowns. And then, the probabilistic analysis actually becomes very, very complicated. So it's difficult to know, like, it kind of sucks because, of course, it would be great to be able to say, okay, if the adversary is a bit weaker, then how does that impact our anonymity? But it becomes very hard to actually have results for that kind of scenario.
Which brings the follow-up question, given the Snowden revelations, do you think that there is a point of discussing such a slightly weaker adversary, given the fact that there are agencies trying to do, let's collect data?
I mean, we do know that some adversaries are able to monitor, you know, globally the network. And I mean, you might as well kind of give a bound on the kind of anonymity you're providing, in the sense that if you consider like a global adversary, then you know that this adversary, you know, is able to narrow down your anonymity set to a certain point, and an adversary that has less information, well, will not be able to do better, right? So in that sense, it provides a bound.
An earlier question, actually, by Gusen, before we go to the next one, which asked about indistinguishability. Where does it fit in your picture? And I think this relates to the basic components of the cryptography.
Yeah. So I think indistinguishability is kind of a concept that is very much intertwined with these properties such as anonymity and linkability and so on. Indistinguishability is, you can use the concept of indistinguishability to construct an anonymity property to say, can I distinguish who's the real sender or not? Can I distinguish if these two messages are related or not? So indistinguishability is conceptually related to anonymity and linkability and even an observability, because it's about distinguishing situations where distinguishing situations where the sender is Alice or Bob, distinguishing situations where, you know, And if you're not able to distinguish that, then you have a good privacy protection. If you're able to distinguish, then the adversary can figure things out and you're not really achieving your goals.
So you always assume that the cryptography is good enough, so have this property, because otherwise...
Yeah, this is distinguishability based on metadata, traffic data, which is based on like lengths, times, and times, lengths, to, from, and traffic data. We make complete abstraction of the crypto.
So Piyush is first of all thanking you for your talk, and then he has two questions, or she has two questions, I'm sorry. When you consider delay here, she's discussing delays in mixnets, we are talking about the network delay of individual packets. However, when we look at the delay at the application layer for applications such as web browsing that require multiple packets exchanges, the overall delay perceived by the end user would be much higher due to the multiple packet exchanges. Is this behavior of delay already accounted for in mixnets? And additionally, when we compare delay with other trilemma features such as anonymity or bandwidth, I think delay might be the only one that have this cascade effect for end applications. What are your views on this?
Yeah, it's an excellent point. If you have applications that you're transmitting longer chunks of data, and you're partitioning this data in packets, and then these packets are sent to the mixnet, they might arrive out of order. So indeed, you might have a delay in the end-to-end application level that goes beyond the latency of individual packets. So indeed, this is additionally kind of adding latency at the application level if you have this out of order delivery, indeed.
So this raises a second question, apologies again. What are your views on the value of delay permissible for end users, or if you have any pointers on?
Yeah, that is entirely application dependent, right? So for example, for web browsing, people are unwilling to wait too much. So this is why systems like Tor that are very geared towards web browsing, they do not add any latency at all to packets because that would hurt usability and users would not be using the system, right? If you're thinking of, for example, file transfer for, I don't know, BitTorrent or something like that, this is running in the background and people probably have, you know, minutes or even hours of latency tolerance. If you are thinking of email, it's probably, let's say, up to a few minutes is probably okay. Beyond that, it starts being annoying. So it really depends on the application. If you're thinking of voting, then it's enough for the votes to be ready by the end of the day, right? So that's indeed a very good question, and it's a challenge in the sense that if you're designing an anonymous communication system that you want to use for arbitrary applications, then of course it's challenging to dimension it in a way that it will be good for all these different applications. Now, I have to say that one way to deal with this is to use continuous time mixes, in the sense that in continuous time mixes, the sender is specifying the latency at each of the hops, right? So it is not unthinkable that you would have different delay distributions being chosen by the user depending on what the destination is and what the kind of application and latency constraints it has. Now, of course, this would provide, I mean, the analysis for this has not been done, as far as I know, although I'm interested in doing it actually. But the thing is that you would get better anonymity than if you have completely separate networks, each for one application, because that would completely partition anonymity sets, right? So imagine you have an application that is latency tolerant and another that is not. And then you say, well, you know, one of them has to have delays in order of milliseconds per mix, and the other in the order of minutes, right? Or seconds and minutes to make it easier. And you could say, well, let's have different networks. So one is for the latency tolerant application, and the delays are seconds, and the other is for the delay the other way around, the delays in minutes, completely separate, completely disjoint anonymity sets. That's probably worse than having both types of traffic go through the same network. Now, both types of traffic going through the same network will not be as good as all packets having the same delay distribution. So there will be some leakage. It will be somewhere in between having all packets being fully indistinguishable because they have the same delay distribution, and having completely separate networks that have no blending of the anonymity sets whatsoever. So that's an interesting thing to look into, like what is this lidar? And if you look at the differential, for example, the difference between the exponential means of the different delays, how does that relate, that distance, to how well these messages blend into an anonymity set or not? So these are all open questions. I have no answer, but I think they are definitely worth looking into.
So this brings actually two questions. The first one you already mentioned. What is the relation between mixnets and electronic voting? Because today, besides what's going on in the US, electronic voting is the thing. We need to vote only via email or via other means. And I know that mixnets are heavily involved there, but what type of mixnets are there?
The original design of Chaum, it kind of generated like two lines of, two fields of research, two subfields of research. So one is the mixnets for email and messaging, which is the thing I've been working on mostly. And these are decryption mixnets, right? So this is this idea that you encrypt multiple times, and then each intermediary has a key and they can take out one layer of encryption, right? The other field of research that was spurred from Chaum's original work was in the area of voting. And those are different systems. Those systems, they have very strong verifiability properties, right? Because you want to be sure that no intermediary is dropping a message or inserting a message or modifying a message. Otherwise, you could have mixes introduce new ballots or delete ballots. So this completely would destroy trust in the voting system. So voting mixnets, they actually have what is called this very strong verifiability, which means that they publish, the communication is done via some public bulletin board, so that everybody can see the inputs and the outputs of each of the mixes. So they communicate via public broadcast channels, effectively. And they publish, together with the outputs, a proof that this set of outputs is a shuffled version of the inputs, and that no modifications or have been done, right? So it's a different, I mean, of course, this comes with other constraints. If you do that, you should probably go for threshold mixes, because doing that with a pool becomes very complicated. They typically also have cascades instead of networks, in the sense that you just have the batches of ballots going from one to the other and having this proof. So, I mean, the application introduces some other constraints, but the key thing there is that you need to have this very strong verifiability so that everybody can be convinced that no tampering has happened.
But would it still be susceptible to sort of like traffic analysis? I want to see the vote coming from you going to maybe according to time or maybe according to other parameters.
So in the systems that I've seen, they are typically Chaumian mixes in a cascade. So that means that you would have an anonymity set of n being the parameter of the threshold of the mix. So imagine you have a mix that takes 1,000 inputs. And it would be a cascade of maybe 3, 4, or 5 of this, you know. So the first one collects 1,000 inputs and then shuffles them, sends those 1,000 inputs to the next one, who shuffles them, and that's repeated multiple times. So your anonymity set would be the threshold of the mix. In this case, the other 1,000 people that are mixed together with you. I mean, obviously, if those 1,000 people, they're all voting the same, then, yeah, then I know what you voted for. But if there's some diversity there, then I will not be able to infer your vote.
Single electee voting is significantly easier. Yeah, a choice, which actually raises the question. So it seems like it's somewhat resembles Tor in the sense that you have layers, and which brings me to the question: have somebody tried to connect Tor into a regular mix? Let's go back to communication anonymity and not elections. So I want to have. I'm willing to get to pay the price of latency. So I'm connecting with Tor to the mixnet, and I'm getting both anonymity guarantees, or it's going to be something completely.
So, I mean, the key difference here is the circuit-based versus message-based, right? So, I mean, it would be possible for Tor to apply latency to the packets within to the packets that is processing. So instead of sending them as soon as possible, keeping them for some random amount of time or batching them in some way or so on, right? Now, the problem is that because it's circuit-based, which is great for efficiency because that means that I establish a shared key in the beginning when I make the circuit, and then after that I just use symmetric key crypto, right, which is very efficient. While in mixes, because of these per packet keys, you have to do public key operations per packet, which is much more expensive. Now, the problem is that what you lose with this symmetric key efficiency is that now you have linkability of all the messages that belong to the same circuit, because the mix has to know that this key is the one that they have to apply to transform this packet. So that means that they are able to know that all of these packets belong to the same circuit. And that is kind of rich information in the sense that even total length, even if you're playing with timings, total length in the case of websites can be actually already a distinctive feature, for example, right? So yeah, having circuit-based and still wanting to have kind of preventing end-to-end correlation attacks is not easy. I think the best chances are using heavy-duty dummy traffic so that one end of the communication is fully padded and you cannot see any patterns there. That's very expensive. Or yeah, otherwise it's not easy.
This is, I think, the one-time pad equivalent for anonymity, right? That
yeah.
You broadcast the same amount of data, dummy data, to make sure that no patterns are available. Are there any other questions? Please put them in either in the chat or in the Q&A. If not, I would like to thank Claudia once again. Thank you very
much. Okay, so people can go to the break early, I guess.
Yes, I think we will take an earlier break. We will reconvene in 20 minutes to hear Alessandro Acquisti talking about the economics of privacy. And I think this is going to be very interesting to see how the money works around and the incentives, because I think at the end this is something that usually as technical people we understand less. And I would like to invite everyone. You have 20 minutes to grab coffee or tea or whatever you're drinking, and see you in 20 minutes.
Okay, thank you very much. Bye-bye.
Bye.